Okay, we're going to go ahead and do this. Sounds like you're on track. Maybe not all the way through, but okay, what can you say? You can say that Q equals, well, first of all, just to, write out the definition. C1 equals Q over V1, right?
Right.
So the Q equals C1 V1.
Right.
Okay? Now I'd start with this. I wouldn't just assume I know this. This is a definition of capacitance, charge over voltage, right? So start with the definition of capacitance. We can say this. So, voltage 2, I call it voltage C2, but it's obviously voltage, what I mean by voltage 2, right? Voltage across capacitor 2. Voltage 2 is Q over C2 and Q C1 V1, so that's C1 over C2 times V1. And you maybe think about how that works out, okay? But you have equal charges. So it follows that you take the ratio of this to this, and you get, well, there's your ratio. You multiply that by your V1, okay? Without going any deeper into it than that. Then V net is what? What's your voltage across the combination? You put a meter across here to here, what do you get? Simplest possible answer.
Q over C net.
That's not the
Or
simplest
V.
possible answer. Look at the picture. What's the simplest possible answer for the voltage from here to here? Put a V here. What's voltage?
Is
Potential difference.
Joules of-
Change. Yeah, well, it's got
Joules
units of
over
joules per coulomb, etc. Right?
right.
What's it mean? It's the change in potential energy from one point to another. What's the change in potential energy from here to here? How does that relate to the change of potential energy between here and here, and the potential energy change between here and here?
Well, in the middle, it's 0, right?
Yeah.
So it should just be the end pieces,
I'm sorry?
the difference of the end pieces.
Difference of the,
End pieces, because the middle is 0.
we're talking about how much work it takes to get a charge from here to here.
Right.
How much work does it take to get from here to here? Well, it's going to be V1 times whatever charge you're trying to move, right?
Right.
How about from here to here?
Yeah, it's
You
0.
move for free. It's an ideal wire, no resistance. Okay?
Right.
From here to here?
It'd be V2 times the charge.
Yeah. So how much work does it take to get from here to here?
V1 and V2 times the charge. V1 plus V2 times the charge.
Yeah. It's V1 times the charge plus V2 times the charge. You use the distributive law and factor things out, right? So V net is V1 plus V2. Okay? And the reason is let's say here's point A and here's point B. Okay? Work to move delta Q from A to B. V1 delta Q plus V2 delta Q. Right? I'm not going to write out all those details, but that's the way you want to look at it. Okay, just line integral of your electric field, etc., whatever. But of course, electric field is only here and here, right? So you go back to whole analysis of a parallel plate capacitor and understand this. Equals V1 plus V2 delta Q. Okay? So, net voltage is this. There's a little bit of a leap from here to here, but you want to be able to reason that out. So that equals
Go get you some little scissors.
V1 plus C1 over C2 times V1. Okay? And that equals Q over C net. Okay? Now if we write this as C1 plus C2 over C2, then with just a little algebra, we see that C net equals and actually I probably want to write it and I haven't written everything out. Reciprocal, C net would be the reciprocal of this, so this would be times V1 over, that's times V1 over Q, let's see. Okay? And V1 over Q is just reciprocal of Q over V1. So, work that out. Make sure I'm right about that. Something doesn't look right, but work it out.